Hi guys, so if you missed the class, that's going to be a short video about static equilibrium and pulleys in 2 dimension. So very simple demo that I did in class. So here I have calibrated my scale, and doesn't matter the unit really. Here you have 200 grams, and that's going to be the weight I'm using. I'm including the pulley here, and you have the holder and the muscles, right? So you have to pull, and so it's in equilibrium here between the restoring force from the spring. The spring hook slow applies and the weight pulling down. So it's very hard to pull up. So we need a machine to help us out. And here I'm gonna take the pulley here. I'm gonna put that here. Okay, like we did in some problem in class. I'm gonna have this here. So still I have 200 down for pulling down. My system here, I'm considering this system here. So it's acted upon by 3 forces, right? So you're gonna have the weight 200 grams pulling down, and I'm using grams, and you have tension here and tension there. If the 2 strings here are vertical, and I'm neglecting the mass of the string, I'm not neglecting the mass of the pulley here because I have included that in the 200 gram. And I suppose that is not stretchable. So what I want to show you is that if I take my spring scale here and I'm pulling it up, so I don't know if you can see the reading here, but what you see is 100 grams. Okay, so it's much easier, of course. So that's why a pulley is a machine, make us stronger. And so because the string are vertical, I'm going to have 100 here, 100 there, 200 down. So there is always a price to pay. Okay, I'm twice as strong. The mechanical advantage is 2. But of course, I will have to pull twice as much to increase the distance here. So if I pull 2 inches, the weight will be moving up 1 inch. So why can we use a second pulley? It's not to increase the mechanical advantage, but let's say the string are still vertical. I'm going to bring this one a little bit here. Now, let's say the string are still vertical here. And you see, I'm still, so now I have this system here. So now you see, if you see the reading here, it's still 100. So the mechanical advantage didn't change. However, because I'm pulling down, it's going to be easier because I can add my weight. Okay, so if it was like a huge system, I can hang there and I can add my weight, so it will be easier. But as long as the string here are vertical, I'm gonna have 100 here pulling up, 100 here pulling up, 200 there down. So that will be my system. And the tension here is transfer. So that's going to be 100. This is going to be 100. Here we neglect the pulley mass. So that's going to be here 100 as well. Right? So the string is just a way to transfer the same force, right? So if you were to make a free body diagram, if you were to make a free body diagram, so then you have the pulley here and the mass. So the whole system here, it's like a system, that's the system you are considering. So then you're gonna have 200 down, so 200. My unit is gram, but you can convert that in Newton if you want. And up, it's vertical, there is no angle, so it's going to be 100 here and 100 there. So if you do the vectors, you see that vector down, so you have 200 gram down equals 100 up plus 100 up. Okay? So let's see what's going to happen now if there is an angle. So now I'm going to make an angle here. So you see the string are not vertical anymore. And what you should see here, so the angle is still the same. Hi guys, so what I was telling you is that you see I have 200 down. If the strings are vertical, I'm gonna have, I don't know if you can see my scale here, but it says 100, so I'm gonna have 100 here. So 100, the tension is here, and 100 there. However, if the string here are not vertical, what I want you to see is that the tension here is increasing. You see, now it makes an angle. So there is an angle here relative to the horizontal. So I'm going to have more tension here and more tension there. So here and there it's going to be more than 100. And this is because a force here, a tension is a vector. So now it has to have some horizontal components. So we need to increase the tension there to have more vertical component there, because it has to contribute here to the horizontal components. So if the angle are the same on both sides, and if I get it to 120 degrees, now you see as I increase here, if I make it 120 degrees, I'm going to have 200 here and 200 there. So it has increased here significantly because I go from 100 to 200. This happens then when this angle is 120. Okay? And you can explain that by using vector and parallelogram method. So here I have 200 down, 200 here, 200 here, in such a way that the vertical component here will be 100, the vertical component here will be 100, so it has to add up to cancel out the 200 down. So I can show you that. So now if you have your weight, so this is your 200 gram weight, and let's say this is 200 gram here. And now you have strain. So let's see, maybe it makes an angle here. So this is the horizontal. Maybe the angle here is 120. So you want to have the tension in the strain, such as if you add the vector, the tension will add up to your 200 here. Right? So it's the condition for equilibrium. So you can make a parallelogram. So it means here, I'm going to make that side parallel to this one, that side parallel to this one. Okay, I'm not drawing on scale, but you can do a better job. But I'm doing it. It's supposed to be a parallelogram. It's hard to draw. And when you add this vector here, so that will be the tension here, the tension there, those two vectors, of course, it's going to be the same because the angle is the same. Those vectors, when you add them up, it will be 200 here. So you see that the tension here has to be greater than 100 because it needs to have some horizontal component here, horizontal component there. So that here tension will be greater than 100. And it will be 200 if that angle is 120. Okay, so that's how it works. So the question is, what's gonna happen now if the angle is not the same on both sides? So here I have like made like in a way. So the angle is the same here, like before, but what's gonna happen if the angle now is not the same on both sides? Something like this. So what you see here is that the tension here will be smaller than the tension there. But if you do that at home, you can feel the tension here is much stronger than the tension there. Of course, you can do the math, but here you see that here I'm reading 100. So this one has to be larger than, of course, 100 larger than 200. And you can do it and show that with vectors. We can show that if it's not great, I'm just trying to show for students who miss the class, but here if you have 100 down and you have a string here almost vertical, but this one is almost horizontal, you can use vector addition to show that the tension here will be smaller than the tension there. So again, you make a parallelogram, so you want to have 200 here. Okay, so that's going to be parallel to this side. That's going to be parallel to this side. So you see that tension here will be smaller than this tension there. Okay, and you can do the math. So the x component will be the same. The y component here will not be the same. This one does not contribute as much. This one contributes more, such as when you add those two vectors, you're going to get 200. Okay, so now it explains why if you're hanging a tree, so let's say you are doing hiking, right? So this is two trees, and you don't want the bear to catch your bag. So you have your bag here. The string can never be horizontal. That's not possible. So if you have a very, very heavy bag here, so that means the tension here will have to be huge. Such as you see they have a large horizontal component. Their vertical component is small, so they have to be huge to be able to cancel out this one. So it's impossible to have a horizontal string, and if your bag is very, very big and very heavy, the tension here will be so large that it's going to break. So that's for people who miss the class. I hope that it was possible for you to see.